basic idea, bonded particle modeling. Now we talk about PFC, which is an embodiment of this concept of a bonded particle model, right? As you know now, PFC is a purely just a distinct element framework, okay? It's a computational engine and it's a graphical user interface, right? And it has these logics that are useful, like the visualization stuff and like the histories and things like that, okay? Um, so it's the same way that like ANSYS is a finite element program. End of story. There's all kinds of different ways you can apply it, just like PFC. Okay. Um, and what does it do? It uses the distinct element method, and it's basically explicitly moving forward in time, and it's solving F equals MA. And you know all about this stuff now, right? Contact forces, equal and opposite. The particles are rigid. They move independently. They interact at contacts. And these contacts are always pairwise. There's always just two things at a contact, right? And as we mentioned, there's a force and a moment that acts at a contact, equal and opposite. In reality, then what we have is we have particles and we have contacts, and so we have the proper science of that is contact mechanics, right? That is done in PFC by basically allowing these things to overlap. We call this a soft contact approach. And as they overlap, we put in springs. And so all of the action happens at the contacts. All of the deformation happens at the contacts. And here's that example I talked about before. Take the baseballs. You've got the idea. Fix them, put them on the floor, put a plate, push down with W on the plate and measure delta. And these things are gonna, because they're, if you have a linear elastic isotropic body and you squeeze it, it will change its shape. And it will have, if you have a non-zero Poisson ratio for that system, it will have an expansion, right? That's what would happen. We don't model it that way. We model it this way, where the shape doesn't change, but overlap occurs, and we put springs at each overlap point, right? Now, here's some new stuff. Notice I haven't ever talked about stiffnesses. I just keep saying 1e to the 8th, and I haven't talked about how in the hell do you decide what this number is, right? Well, we're going to find out here that the stiffness can be related to this idea of an effective modulus. Think of it this way. I'm going to take this discrete system, and I'm going to conceptually pretend that this discrete system is this. What's this? This is, and this is, think of this as 3D. This is a circular cross-section cylinder, okay? And this cylinder goes from the center to the top of the particle. This cylinder goes from the center to the center, okay? This cylinder has a cross-sectional area A, and it has what I'm going to call an effective modulus, okay? What we're saying, and then what we're going to be able to do is we're going to be able to relate this stiffness to this effective modulus, okay? And so the way we're going to do that is this thing here. If we take a cylinder and a spring, we can show that the stiffness in the normal direction of a single spring is going to be AE over L. And I don't know, do I have the formula? I don't show the derivation of that. This is, we can show this, okay? So this is saying that that's the relationship. If that spring, if I want, think of this as if I had this system and it was in a black box and I could not see what was inside here. If I choose the stiffnesses here such that it's equal to AE over L, where the input parameter is E, I will find that that is the value of E that I will measure if I do a test on this. Okay. So this is what we typically do when we assign the stiffnesses to the system. What we do is we have this, we call it a deformability method. We specify two things. We specify the effective modulus, and we use the effective modulus then to get Kn. So it's AE over L. What's A? A is going to be, here's a ball contact. It's going to be this cross section with this length, 2 small r, pi r squared. L, this is going to be L. It's as though this spring is supposed to behave like a cylinder cross section hunk of material between those two guys. Okay. And so by doing that, that's how we're going to set Kn. And then we're going to specify a normal to shear stiffness ratio, which we're going to designate as kappa star. And then if we know that, we can get Ks because it's Kn over kappa star. So these are going to be the micro properties that we are going to specify for our system. One of the things we find, if we work through this, and I'll do some of this tomorrow, is that if you have a collection of 3D spheres, okay, and if you do this for choosing Kn, the overall macroscopic modulus you measure will be very close to E star. And if you change the size of the spheres, it will still be equal to E star. This relationship, what you're going to find is if you change the size of the spheres, you're going to change Kn. If you were to just take a bunch of spheres and set Kn constant and measure the modulus for one, and then make a bunch more spheres that are smaller and set Kn the same, you're going to get a different modulus. Okay. Why is that? Let's just do a quick thing here. I don't have a blackboard, so I have to do this. Come on. There we go. Stiffness equals A E E star, the equivalent modulus over L. Now, if I have a cylindrical cross section A and the disk radius is this is going to be pi r squared. There we go. R, it's going to be the minimum R. Pi r squared is the cross-sectional area of that cylinder. The length is going to be 2r. And notice this then is going to be an R left over. So we're going to get pi r over 2. Notice the stiffness we're going to set then is going to be different depending on the radius. And if we did this the other way, right, we could have written that E star equals KL over A, right? Right? So the modulus will be different if we choose K, right? This, what's this? E star equals, well, help me. K times 2R, K times 2R, K times 2R over pi R squared. Right, which equals K times 2 over pi R. Did I get that right? We'll actually demonstrate this tomorrow. We're going to build a synthetic sandstone, and we're going to first just set Kn to be constant. And we'll build two specimens, one with a certain size radius, and we'll measure E, okay? And then we'll build another specimen that's got smaller balls, and we'll measure E. And we're going to see that we're going to get different values of E. But if we specify E star, that's the same for both, we're going to find out that we're going to get the same value of E, okay? So by doing this, by using these two parameters, we're able to get a size independent modulus out of our system. So these are going to be the parameters that we're going to specify as microstructural parameters. Okay. Then here's what we're going to find. Now here we take an assembly, we squeeze it, and we apply confinement. There's my triaxial test, right? We're going to find that the measured modulus of the whole system is going to be basically proportional to E star. And so if we increase E star, we're going to increase the modulus, right? So what you're going to do then, build a system, set E star equal to the desired E of your real rock, do a test, measure the modulus, and you're going to say, oh, I'm off by 15%. Then you're just going to change E star by 15%. You're going to run the test again and, oh, I got it. Okay. Now, the other thing that isn't at all obvious is that the Poisson ratio that you're going to measure is actually related to kappa star. Okay. And what's going to happen is the Poisson ratio is going to increase to some limiting value as you increase kappa star. Okay, why is that? Here is the basic mechanism that's going on. Okay. This is a collection of discs that were perfectly hexagonal packed. And here I'm just pulling out one little representative hunk of that. Okay. And what I'm going to do is I'm forcing this top guy to go down and this guy to go up. And these guys are bonded. Okay. And the bonds are infinitely strong. So we get no breakage because we're trying to measure an elastic property. Okay. What we're going to find is that if this ratio, this is kappa star, if this is greater than 1, these are the force chains. Okay. And so notice when I squeeze this force chain is going a little outward, which means this guy's going out and this guy's going out, which means there's a positive Poisson ratio. It turns out if you set this ratio less than 1, the force chains look like this. You can kind of think of this, right? If I push this down, this surface is making a shear go this way on this guy. It's sucking in. That's really what's happening. And this is a negative Poisson ratio. And if you choose Kn over Ks to be equal to 1, the force chains go dead straight. And if the force chains go dead straight, that means there's no expansion or contraction. And you get a 0 Poisson ratio. Okay. This is a whole entire lecture that talks about that. And this is not the lecture. This is actually the answer to the exam question, which talks about that right here. Okay. So you can read that for more detail. And though, I want to show you a picture of this from grad course materials lecture notes. Here we go, lecture notes. There's a whole section here about relation between Kn over Ks and effective Poisson ratio, number 14. And so, oh, is this my lecture notes? Yeah, there we go. You can work all this out. I want to show you a picture here. Sorry that it's sideways. This is running PFC with this problem. And if I got to rotate this, I'm going to lose my mind. How do I rotate this thing? Can't I rotate? Oh my God, it won't let me rotate pages. Sorry about this. Well, we're squeezing it this way. If Kn over Ks is 1, the force chains go like that. If Kn over Ks is greater than 1, it pushes them apart. And if it's less than 1, the higher Kn over Ks is, the more it pushes apart. And if you go the other way, where Ks is bigger, it sucks it in. Okay. And you can see this. This is an analysis that applies to the whole packing because this is a representative chunk. So there's a system of disks. Kn over Ks is 1. They're getting squeezed. Notice the force chains are going straight through. So there's no expansion. I push it and these guys just move in and move in. There's no Y component. Now you can just see they're just getting pushed from the top. They're moving straight down. Now I go and I change Kn over Ks. and I start getting this Poisson effect going out. And if I do it the other way, I start getting this thing sucking in. Okay. Now, all that being said, what we find is that, so this is for a perfect hexagonal pack. So if you make a perfect hexagonal pack, and if you set Ks smaller than Kn, you will measure a negative Poisson ratio. So first of all, it is okay to have that. Energy considerations are such that the Poisson ratio has to be between -1 and plus 0.5. The vast majority of real materials have positive Poisson ratios, but there are real materials that have negative Poisson ratios. Okay. Those negative materials, it turns out, microstructurally are exhibiting that because of this effect. Okay. And you have to build weird materials where the shear stiffness is greater than the normal stiffness at the interfaces between them at the microstructural level. Think of your hand again. If you hold your hand out in front of you and you make a fist and you push down on the back of your hand, the normal stiffness is much greater than the shear stiffness. That's almost always happening. So when you take, so if you have a perfect hexagonal pack, you will get a negative Poisson ratio if you set Ks less than 1, let Ks greater than Kn. However, if you take an arbitrary packing and you do this, you will still get a positive Poisson ratio. And what you will see is, as you play with this thing here, you will see that you will eventually get to some value, and the Poisson ratio is going to go from a small number, and as you keep increasing this, it'll go to some limiting value, like say 0.3 or 0.32 or something. Okay, I've said a lot of stuff, and I know I haven't said it clearly enough, and I wish I had a blackboard and I could talk with you, but do you get the general idea? You know about this now, 4 entities, right? Particles, balls, clumps, rigid blocks, they obey the law of motion. There's an example of a bunch of pebbles, and the more pebbles you put in the clump, the closer it is to representing a shape. These are the rigid blocks, right? There's walls, which are surfaces that have velocities that interact with these guys, and then there's contacts, right? Force and moment. Okay. This is just pointing out that this is what a PFC 2D model is. It's unit thickness cylinders, as you can see here. Okay, it's not really, it looks like when you do a biaxial test, it really is a test on cylinders. It's not a test on a cylindrical thing. It's cylinders. Like, for example, when I squeeze the cylinders, in reality, they're supposed to squeeze outward, and there should be confinement that naturally builds up on if you had walls on each side, but that doesn't happen in the PFC 2D system. If you have a triaxial set of spheres in a cylinder and you squeeze it, it bulks out in all directions naturally because it really behaves like a bunch of spheres in a cylinder, whereas 2D doesn't. Okay, so that's something to be kept in mind. Here's what I'm trying to argue. The PFC model, I think of it as an actual synthetic material. What do I mean by that? I mean rigid grains interacting at contacts. And that statement is a vast microstructural space, okay? Because we can change the grain shape, right? We can change the contact behavior of the bonding. We're going to find out there's different contact models for very particular reasons. Right, we have granular systems, we have bonded systems. As the bonds break, they turn into granular systems, right? And we have this ability to put an interface into the bonded materials so that they're not bumpy. And I'm saying that we have these different types of bonded materials, and there's more than this now that I'm going to talk about. But we have this idea. We talked a little bit about contact bonded. We talked a little bit about parallel bonded. We also have another type of bonded thing called flat jointed, which we'll get to. And so there's basically 2 types of things people are doing with these models, right? They're doing practical things, looking at boundary value models. I don't know, looking at sand production around a hole. And there are also a lot of people are doing fundamental rock mechanics research, by varying different aspects, right? What's the effect of grain shape? What if I change cementation? Is that closer to this sandstone or that sandstone? Stuff like that. Okay.